Hey, future PTAs. Today we're going to talk about thermal agents and talk about specific heat and the modes that heat transfers. So specific heat is the amount of energy required to raise the temperature of a given weight of material by a given number of degrees. It's expressed in joules per gram per degree Celsius, JGC. And the specific heat of different materials and different body tissues differ. So skin has a higher specific heat than fat or bone. Water has a higher specific heat than air. Specific heat in various materials. So materials with a high specific heat require more energy to heat up. So water would require more energy to heat up than air. But they also hold more energy at a given temperature. So when we're transferring heat to a patient, thermal agents with a high specific heat are applied at a lower temperature than thermal agents with a lower specific heat. An example is moist heat pack versus fluidotherapy, which is an air-based therapy. And so moist heat has a higher specific heat, and the heat transfer actually goes to deeper layers of tissue than heat transfer through air or through fluidotherapy. Different modes of heat transfer that we're going to cover are conduction, thermal conductivity, I didn't realize it was a little over to the side, convection, conversion, radiation, and evaporation. So conduction, this energy exchange is by direct collision between the molecules of two materials at different temperatures. So the energy exchange happens in materials that are touching. It requires direct contact of the targeted area with the heating or cooling agent. Heat is conducted from materials at a higher temperature to lower temperature. So if you have a hot pack on, the heat is being transferred from the hot pack to the body. And if you are sitting in a bath of ice, like that top picture, then the heat is being transferred from your body out to the ice. So you're losing heat if you are surrounded by ice. You're gaining heat if you're in a hot tub. Thermal conductivity, that's the rate at which the material transfers heat by conduction. So this is kind of a subcategory of conduction, or an explanation of the rate that conduction happens. The rate which the material transfers heat by conduction. Depends on the temperature difference between the materials, their thermal conductivity, the area of contact. And it's expressed in an equation here. You don't need to memorize the equations, but that's just there for your excitement. I'm sure you love it. Metal has a higher thermal conductivity than bone, muscle, or fat. Water has a higher thermal conductivity than air. So if you notice, when you're dealing with something metal, it gets colder faster and changes its temperature faster because it has a higher thermal conductivity, the rate at which, or the speed at which the material transfers heat, the energy is transferred. So when we use conduction to heat patients, in order for it to be safe and effective heat transfer, it requires materials with a high specific heat, a moderate thermal conductivity, materials that are well tolerated, and the initial difference in temperature, so you don't, that's why I have this picture here. It's not like a shock to the system that you just are covered in ice and you have to jerk back and it's too much, but something that kind of begins slowly and then transfers the material so that the patient can tolerate it. Insulators such as towels are sometimes required to hold the air to limit the rate of heat transfer. And then removal of metal jewelry from an area that will be in contact with a conductive thermal agent to avoid excessive local heat transfer. So remember, metal conducts energy faster. So if you have heat or ice over an area, ideally they need to remove, not just ideally, they do need to remove their jewelry from that area, or they could possibly get a burn or something like that in that area. Rate of heat transfer, here's another formula for you to read, but you don't have to necessarily memorize. but things that you need to understand: the greater the temperature difference between an agent and a body part, the faster the rate of transfer. So if you put something that's a little bit warmer than body temperature versus a lot warmer, the transfer rate will be different. The one that's most different than the body temperature will be faster. Materials with high thermal conductivity transfer heat faster than those with low thermal conductivity. And then the larger area of contact, the greater the transfer. So if you're submerged in ice, there's going to be a lot more heat lost than if you just have a little ice pack on your shoulder. And then the rate of temperature rise is proportionate to the thickness of the tissue. So the deeper the tissue is, the less its temperature will change. So that's why I have this picture on the side. If you have hands that are submerged in ice or holding ice, the temperature of those hands that have very thin amounts of tissues covering them is going to change a lot faster than if you have a more fatty body part submerged in ice. Okay, so the thickness of the temperature also, of the tissue also changes the temperature transfer and how quickly it's able to transfer and how deep that transfer goes. Convection is a different type of heat transfer, different mode. This is heat transfer by direct contact between circulating medium with another material of a different temperature. It transfers more heat than conduction. Some of the examples are whirlpool or fluidotherapy. So here's whirlpool, where kind of like being in a hot tub where you turn the jets on and there's water swirling around you. That actually, the convection, the swirling motion around you, transfers the energy faster. So I really like this picture here of someone cooking where convection is happening inside the water. As you see it come to a rolling boil, what's causing that water to roll as it boils is convection. So it's that whirling, circulating motion that's causing it to transfer heat faster. The heat that comes off of the stove that's not necessarily going straight into the water, the additional heat is radiation. And then if you touch the hot surface, the heat that goes into your hand is through conduction. So things that touch are through conduction. The circulating heat is through convection. And then that radiating, the extra particles that you can just be near and feel the heat, is the radiation. Another example of convection is circulating blood that helps maintain physiological temperature by convection. Conversion is another mode, converts non-thermal forms of energy into heat. Mechanical, electrical, or chemical energy are some of the things that can create conversion. So an ultrasound is an example of that. It converts mechanical vibration into heat. Diathermy converts electromagnetic energy into heat. Metabolism within your body converts chemical energy into heat. So all of those take a source that's not hot itself and convert it into heat. Unlike heating by conduction or convection, the temperature of the thermal agent isn't important because we're not using that temperature, we're using what it is converting. It does not require direct contact, and it may have other effects beyond just heating. Radiation is a direct transfer of energy without the need for an intervening medium or any contact. Okay, so this is just you're standing near a fire and you feel the heat. That's through radiation. If you're sitting outside and the sun is heating you up or blistering you, that is through radiation. You don't have to be touching it. You don't have to be submerged in it, anything like that. It's just indirect contact that is causing it. So examples are infrared lamps, the sun, transfer heat by radiation. Rate of temperature change depends on the intensity of the radiation, the relative size of the radiation source, and treatment area, and the distance and angle of the radiation to the treatment area. So if you have a really big bonfire, it's going to put off a lot more heat than a really small fire. If you're standing closer to the fire, you're going to feel a lot more heat than if you're standing far away, and things like that. So that is radiation as a mode of transferring heat. Evaporation, this is where energy is absorbed to change a liquid into a gas or vapor. So the material that contributes energy for evaporating liquid is cooled in the process. So as the liquid evaporates, like let's say you have sweat and the sweat evaporates off of you, it helps cool the tissue, the skin that the sweat was touching before it evaporated. Some of the examples are a coolant spray or sweat evaporating, and when it evaporates, it cools the skin that was heated and caused it to turn into vapor. So the skin heats that enough to cause it to turn into vapor, which allows it to be cool. Ambient humidity impairs evaporation, so the humidity of the environment that you're in does change how much that can evaporate, which is why on a hot day, if it's really humid, it feels a lot hotter than if it's the same temperature and not humid. All right, I will see you in the next lecture.